flyboards, and the flyboards are just taking a jet ski, as you saw in the second video, instead of having the water flow out going through a controllable jet for guiding the jet ski. You realize I can just take that off and redirect my powerful water pump into a hose and then bring that up and go into the rocket stuff. So this runs on the same principle as a rocket. Now, based on what you saw, how would you describe how those flyboards work? Okay, you said water pressure. Any other answers?
Seems like there's some equal and opposite force kind of stuff going on because you're spraying water down and that's pushing you up kind of thing.
Equal and opposite, you said water force?
Some kind of force. Yeah, water.
Well, yeah, you just said force. There, I'll put equal and opposite force. Any other ideas? Okay, well, get your clickers out because we're going to have a clicker question here about just this. So the question is, what provides the acceleration of a rocket? Now that's about a rocket, not the flyboards. But it turns out the two are predicated on the same thing. Is it Newton's first law of motion? The one that says object has constant motion unless acted by a net force. Second law of motion, change in momentum of a rocket. Fuel provides force to propel it. Third law, force of a rocket in the atmosphere causes force of the atmosphere on the rocket. Or Newton's law of universal gravitation. Force of gravity, sorry. And, okay, as luck would have it, I see that 7 people responded. What I don't see is their responses. Show the grid. There we go. Well, I can see who's answered now. Hey. Okay, everybody has answered, and nothing is showing me what you answered. Excellent. That's a thing of beauty. I can't see what you answered, so I can't tell you if you answered right or wrong or how many people answered what. That's because I changed this to using 2 monitors. Let's see what happens if I try to change it to 1 monitor on the fly. Nah, that didn't help. Okay, well, here's your answer. Well, actually, before I even give you your answer, I didn't show the quote in today's lecture, but I often do. They're back in the race to send rockets up into the sky. There's an editorial published by the editor of, I believe it's the New York Times, that was chastising the U.S. government for buying into the bunk that was being proffered by, who's the father of rocketry? There's a space center named after him. German dude. Can't remember his name. Well, the bunk that was being offered by him, saying that students in high school physics across the nation are learning enough physics to know that you can't have a rocket work outside of the Earth's atmosphere. That in order to have the rocket move away from something, it has to push off of something else. That is Newton's third law. For every action, there's equal and opposite reaction. So for the rocket to have a force to make it go up, there must be something there for it to push off of. And it wasn't until, 50 years or so later that they published a retraction saying, yeah, our editor was wrong. The rockets turns out do work. So it seemed obvious to that editor, obvious enough that he made himself famous for not understanding physics, that he published an editorial saying that we were wasting money on this idea of rockets. because he thought that it worked on the principle of Newton's third law. So, based on what I just told you, it must not be Newton's third law, because when you get into outer space, that is, you get out of the Earth's atmosphere, there is nothing for the rocket to push off of. So, if it's not that, what is it? Well, the rocket is not traveling with constant velocity, so it's not going to be Newton's first law. So it must be, and it's clearly not gravity, so it must be Newton's second law that is governing what's going on with the rocket. And we saw that clearly with the flyboards. You had water that comes and goes out of those jets, and what is the... Let me draw a simplified picture to make this a little easier to relate. Let us suppose that the water comes in going like this, and then it goes out going like that. So you have that manifold with the jets, and so that manifold is simply redirecting the water so it goes from horizontal to down. Right, so the water is shown with the two arrows. Oh, okay. That is a function of using the mirror cast. Remember, I had a crash. Well, you didn't see the actual crash, but I had a crash using the other one. It told me Google Play Services is no longer working. I don't know what was going on. Okay. So, what direction was the momentum initially in this picture? Okay, so we had momentum initial is to the right. What direction is the momentum at the end? Momentum final is downward. Now, it's the same water with the same velocity magnitude, the same flow rate. So, the magnitudes of those two momenta are the same, but the directions are not. So if I was going to calculate the change in momentum, what direction will the change in momentum be? That's not a P. What will I get for the change in momentum? How do you subtract vectors? Yeah, the one that's negative I turn backwards. So I'm going to start with P final, which is downward, and then P initial was to the right, so I'm going to add a negative P initial, so I'm going to go like this. So here's momentum final, and here's minus momentum initial. What do I have for my resultant there? What direction? Down and to the left. So there's my change in momentum. So the change in momentum for the water was down and to the left. Now there has to be a net force to cause that change in momentum. And Newton's second law told us that the net force is equal to the change in momentum divided by the change in time. So if I can make that momentum change quicker, which would happen by having either more water per second, more mass per second, or higher speed, the two things that would affect this, then I can get a bigger force. And that net force is going to have to be the same direction. So I am providing a net force on the water that's pointing this direction. Now, Newton's third law is going to come into play because the water, our propellant, has to have a net force pushing it down and to the left. So what direction is the net force provided by the flyboard? Oh, excuse me. What direction is the net force of the water pushing on the flyboard? It's going to be equal and opposite by Newton's third law. So the net force on the flyboard is going to be like that, pushing the person up and forward. Now, of course, if the person doesn't want to go forward, they'll have to kick this so it goes a little bit in this direction so that it's you know, making it so your net force is vertical. Question?
Why does the flywheel go that way again? Of the force of the flywheel.
Okay, the water had a change in momentum that's going from like this to like this, right? And so the change in momentum of the water was going in this direction, which means the net force of the flyboard pushing on the water was that direction. Newton's third law says the net force of the water on the flyboard must be equal and opposite to that. So the water was pushing the flyboard that way. So that's the basic physics that makes those things work. And of course they had little things on the hand so you could have a little more control and make your upper body do things different than your feet. And obviously when you watch that, they were doing things like a porpoise, you know, coming out of the water and diving back in. And it looks awesome, although I imagine it's got to hurt the head just a little bit. It's exciting, right? I want to do it. Huh?
It looked like they were like 20 feet in the air. That's a pretty solid slam.
Yeah, especially when you turn over and you jet yourself down in, not just fall. Now, why was the hose kind of floating up in the air? You know, they come up and do a loop, and the hose kind of floats up behind them. Why is that?
It's full of flowing water, too.
It's full of flowing water, and that water was going up. Even when you go down, you still had water going up that's trying to make the hose go up. And so it kind of lags behind. You might have seen one of the coolest demonstrations I've never done is to just take a beaker and put some kind of very thin chain in there, and then you just pull the chain over the side and let it start falling. And as it starts falling, it starts picking up speed, and the chain coming out of the beaker has to go up. And as it picks up speed, it's going faster, and it starts flying up and out and over. And it's kind of counterintuitive, right? You don't expect it to fly up and go higher than the edge of the lip to go down. But it's the same idea. It has to have this upward momentum to get out of the beaker, and it can't instantly change. And so it's going up over the edge. And one of these days, I'm going to actually get an appropriate change so I can do that demonstration because it's really cool. I know I could show you, but we only have 20 minutes left, and I have to get to the standard rocket problem. So, what's the standard rocket problem, you ask? Glad you asked. You asked, right? Right? Yeah, sure, whatever. So, here's a picture from NASA. Who better to give me a picture of how a rocket works? Except for there's a lot of better artistic renderings. The basic idea of a rocket is you have fuel in that rocket. And you burn the fuel. You have a rapid oxidation event. With the rapid oxidation, you have heat generated. That heat makes things go faster, makes them expand, and so you have the fuel come flying out of your nozzle. And if you make that nozzle so it directs the fuel that expands in one direction, then that fuel started with initial momentum of 0, and it ends with momentum that's flying out the back of the nozzle. So this burnt fuel had a change in momentum that was going to the back of the rocket. But if this rocket is isolated, the net force on the rocket is going to be 0, right? You're out there in space, there's no air around you. Assuming we can ignore gravity, which for rocket problems we'll say, okay, ignoring gravity we have this, now if we add in gravity we have this addition. So ignoring gravity to start with, we can ignore gravity. The net external force in this rocket is 0, nothing acting on it. And so since the force net is equal to change in momentum over change in time, if the net force is equal to 0, then that means the total change in momentum has to be 0, but the fuel's change in momentum was to the right. So what direction does that change in momentum of the rocket have to be? It has to be to the left. So the change in momentum for the rocket has to be that direction. And that's what makes the rocket go. It's that conservation of momentum. And of course, you need a force to cause an acceleration. That's what Newton's second law said. And that force comes from the force pushing the fuel out. The rocket pushes the fuel out. In turn, that fuel that's being exhausted is pushing the rocket forward. Now, we of course, being a calculus-based class, must be compelled at this point to say, mathematically, how can I work this out? I hope you have a compulsion like that, or at least a curiosity. I certainly did. So, if we're going to work this problem, we start off by saying, okay, the rocket in reality is not going to be locked on a lab bench and stationary. It's going to be out there moving. And we're going to treat our rocket as if there's no gravity. Like I said, after we figure out what's going on, if there's no gravity, then we can just add the effects of gravity. So if there's no gravity, we have this rocket that is traveling with an initial momentum of the mass of the rocket times velocity. But then the rocket kicks out some fuel. So my simplified picture, here's the rocket. And here's a little piece of mass. So that little piece of mass has mass dm. The total mass of the rocket initially was mass m, and dm was part of it. But then it's going to exhaust that dm, so this is going to become, here's my rocket again, but now the dm is out here, traveling at the speed of v exhaust. V exhaust is the speed relative to the rocket. So if I'm going to include the speeds, my rocket started with a speed of v. And it's going to end with a speed of v plus dv. dv is how much it sped up. And so the speed of the exhausted material is not actually going to be just VE. In fact, it started at the speed of the rocket, so it'll be at V plus dV, but then minus the speed of the exhaust with respect to the rocket. So that's going to be the speed of that exhausted fuel. And what mass am I left with here in the rocket? The rocket is left now with mass m plus dm. Now you look at this and there is a sign difficulty. I think I have it written, yeah, right here. A technical but confusing note. Sign conventions say that the new mass of the rocket is m plus dm, which I wrote down here, m plus dm. That's our sign convention, the mass plus the change in mass. But of course the change in mass was negative because mass was ejected from the rocket. So dm is actually a negative value, which means the mass of this ejected piece is actually minus dm. Because dm is a negative value, of course that ejected piece has to have a positive mass. So it's minus dm. It's a confusing thing, but it's a technicality that you have to pay attention to or you're going to get a wrong answer. So we have momentum is conserved. No external force, so the change in momentum is zero. The momentum you start with is mv. The momentum you end with is this long thing. Now let's take this long thing and this will not simplify it, multiply through. So if I multiply through, m times v is mv plus m times dv plus v times dm plus dv dm. Okay, so I multiplied in blue is everything in the first set. And then I'll change to red for the second set. There's a minus sign here, so I'll have minus, and let me put terms in the places that make the most sense. There's a minus VDM, so minus VDM. That's these two terms. There's a minus DVDM. That's these two terms. And then there's going to be a minus and a plus VEDM. Well, trust me, it's all here. Yeah, that's actually why I've been using this rather than that for my connection, because of problems like that. I had hoped they'd be better, although I'll probably have to reboot my tablet before things work right again. So there I've expanded out, and I have to include all of those terms for my momentum final. But from what I've written, you can see, okay, this and this, you probably can't see. These two clearly add to 0. Likewise, these two also clearly add to 0. And so my momentum final is just mv plus mdv plus vedm. Since momentum final has to equal momentum initial, I'm just going to write that as a continuation here. And so it's coming up there. So I have the momentum initial is equal to the momentum final. It's going to show up. Now, with this, I'll go to the next slide. Has it shown up yet? Yes, it has. So going to the next slide, which is the last slide. Now I can't. Okay, that's clearly got to be a problem with using this technology. I can't slide it anymore. So my equation was mv is equal to mv plus it's going to show up. Wow, this is slow. I wish I could make it fast for you. There we go. So that's my equation. Notice I have mv on both sides. We should probably subtract that out. And then that will give me, moving things across, the equation that says mdv is equal to minus vedm. And once again, you're going to have a delay, but that's going to come up. Now we define the thrust as shown here. The thrust is the mass times the acceleration of the rocket. mdv dt. dv dt is the acceleration. Well, if you look at the equation on top, I have mdv. So if I just divide both sides by dt, I would have the thrust is mdv dt is minus ve dm dt. So that's where this equation is. Now you see I put R here. R is the burn rate, the rate at which you're burning fuel in your rocket. So the bigger R is, and the bigger the speed that is being ejected, the bigger the thrust you get. Does that make sense? Comes back to exactly the same thing that we had with the flyboard. If you have the water going faster, or if you have more water per second going through, you're going to have more thrust. Those are the same two parameters we have here for the thrust. A higher speed for the ejected fuel, or a higher rate at which we're burning the fuel. Yes?
What did you say R was again?
R is the rate of burn. R is defined as, remember that 3 lines mean defined as, minus dm dt. Why minus? Because that gives you a positive value because dm is negative. So R is how much fuel per second is being burned. So measured in kilograms per second. Now this last equation is the equation to find the speed of a rocket. Question?
Just to clarify, the m is the initial one, right?
In the equation that's in the square box, m is the mass of the rocket at any time. So it changes over time, and we have to take that into account for this final equation. The final equation to find the speed as a function of time, I'll come back to the red portion of the equation at the top. So writing that equation at the top, again, just the red portion, it was mdv equals minus ve dm. Because of this lag, I'm going to go to technology number 3. I know this is ridiculous, but as I do a derivation, which the next one has a little bit of work, it just doesn't work for you to not be able to follow it in real time. Turn that off. Turn this to 2. And come on. There we go. Okay, now this will be real time. So I have mdv is equal to minus ve dm. I want to solve this for v. What have we done in the past with a differential equation like this? We blanked blanks. Separated the variables. So what are the two variables? M and V. Now notice V sub E is a constant. That's the speed of the exhaust with respect to the rocket. That's a constant. So that's not one of my variables. So I just want my dV on one side, my dm on the other, and the m has to be on the same side as the dm. So a quick rearrangement gives me dV equals minus VE dm over m. Now the left side only depends on V, the right side only depends on m, and I can integrate the two sides independently. So the left side I will integrate from the starting speed to the final speed. The right side I will integrate from the mass the rocket starts with to the mass the rocket ends with. Yes?
The V is a constant.
The VE is the speed of the exhaust with respect to the rocket, so it's a constant.
Doesn't change.
Yeah. Well, the left side is real simple. What do you get from integrating the left side? Yeah, just V final minus V initial. The right side minus VE. What do you get for the integral of dm over m? Natural log of m. Now when you take your limits, that's equal to minus VE natural log of m final over m initial. Well, we don't like having the minus sign in there, and there's a real quick and easy way of getting rid of the minus sign, and that's to flip the two arguments in the natural log. Log of a over b is minus log of b over a. So I can rewrite this as v final minus v initial equals the speed of the exhaust times the natural log of the initial mass divided by the final mass. And then the last step, of course, let's add the initial speed to both sides. And we have the final speed of the rocket is equal to the initial speed of the rocket plus the speed of the ejected material, natural log of the mass it starts with, divided by the mass it ends with. So there's an equation to give us the speed of a rocket. Now notice the mass initial is always bigger than the mass final for the rocket because you are burning that fuel and ejecting it. So that means the natural log is always a positive value. In terms of fuel, what would give you the highest possible speed for the rocket? If you what?
You say in terms of fuel?
Yeah.
Light fuel?
Actually, if you burn all of it, if your entire rocket is made of fuel, and you burn the entire rocket, in theory you would reach infinite speed, right? Of course, you can't make your entire rocket full of fuel and burn the entire rocket. And if you did, well, the payload would be burned too. But if you can make the fuel a bigger percentage of the mass and burn more fuel, leaving less rocket left, you'll achieve a higher speed. So with rockets, the percentage of your mass that is fuel you're going to burn is basically what sets your maximum speed, along with things like that ejection velocity. Now I got 2 minutes. How many people have watched the movie October Sky? Wow, one. It's really a cool movie. It's clearly a nerd movie. It's about some boys in a coal mining town who decide that they want to make a rocket. And so they spend a lot of time trying to develop a better rocket, and they do things like blow up the rocket. But in the end, they make a rocket shoot up in the sky, and the whole town is impressed. The boys figure out how to make a rocket. Now, you think about it, it's probably not super impressive, except for the time they were doing it, this was new technology. And one of the things that they figured out along the way was that the nozzle is a very key ingredient to a rocket. Because you have to have all of that material going the same direction, which is the opposite of the direction you want the rocket to go. If you don't have a nozzle that directs it the same direction, what happens? Well, yeah, you spin around. If you have things going out to the side, they're carrying momentum, but the stuff going out to this side, stuff going out to this side, you're going to just have that momentum add to zero for the sideways momentum. And so you're losing all of that, and you get very little thrust. But if you can get it directed all directly back, then you have better thrust. Because it's, your VE is all going the correct direction. So the design of the nozzles in a rocket is a very important aspect of rocket design, something that they spend a lot of work on trying to optimize the shape of that nozzle. And the size of the hole, one of the things they do in it is they put too small a hole, the pressure inside the rocket builds up too high and it blows up, right? Because a bomb occurs when you build up too much pressure inside something. You put something that burns inside a pipe and cap both ends and burn it, you build up too much pressure for the pipe to hold, and it goes pop, and that becomes a bomb. Whereas if you had a hole and a nozzle, it would be a rocket. Okay, we're out of time. This concludes our rocketry discussion. For homework, probably that's due Friday, I'll try to get a rocket problem in there.
So, Dr. Hogan,
Yes, sir.
off the top of your